My name is Kraig King, and I am a second-year PhD candidate in the Spatial Information Science and Engineering program at the University of Maine. I am also a member of the IGERT Cohort 4 for Sensor Science and Informatics. I'm going to discuss a little bit my research on tiny models. As the field of geosensor network research matures, the number of sensor networks deployed to collect data for geospatial phenomena is increasing. This trend is spurred by significant advances in wireless communication, the miniaturization of computing and storage hardware, as well as advances in sensor materials and technology. However, little progress has been made on decreasing power consumption and increasing device runtime. Recent research in the fields of computer science and spatial information engineering have focused on methods to increase battery life by performing in-network aggregation and boundary detection. Although these methods have proven more efficient than raw data collection, significant power drain still occurs due to frequent radio communication between sensor nodes. I am working on a novel data collection strategy for wireless sensor networks that utilizes tiny models of a known process to improve network efficiency. These tiny models are derived from much more complex engineering models, which are miniaturized such that they can operate within the limited resources provided by current data collection hardware. The intellectual merit of this work is that it revolutionizes methods for sensor data collection by leveraging models of an expected process to minimize unnecessary data collection. Sensor nodes no longer need to exchange information with other nodes, yet the process proceeds as expected. Thus, instead of observing the obvious, the sensor network only initiates wider spread activity in situations where there are measured deviations from the known model, which is event detection. This strategy changes the way current sensor networks are deployed by utilizing predictive process knowledge of the observed phenomena to empower nodes to act autonomously, reducing radio communication. Consider, for example, monitoring the intensity of light over a finite region, for example in indoor space, which is illuminated by a controlled light source. The phenomena of the light distribution follows an expected physical process, which can be captured in a formal model. In order to minimize data collection in the sensor network, sensor nodes do not need to exchange information with other nodes if the predicted process proceeds as expected. The sensor network only initiates wider spread activity in situations where there are measured deviations from the known model, for example, if an additional light source is added. The broader impact of this model-based data collection strategy is that it can facilitate efficient advancement of knowledge within any scientific field which is data-driven. Statistical process analysis and control will no longer become an exercise in data filtering and mining in order to capture events. Only events of interest will be transmitted and stored. Additionally, the accuracy of the sensor network will likely increase due to the higher sampling precision permitted by the minimized power drain. This strategy is currently being tested with numerous simulations, and preliminary work has been accepted by a peer-reviewed journal. Ongoing research will explore the ramifications of various model configurations and network topologies on the performance of this tiny model framework. Through additional exploratory research and synergistic partnerships with external academic departments, it is expected that a broader understanding of the measured phenomena, as well as improved strategies for model-based data collection, will be discovered.